Okay, hi everybody. A very good evening. I hope you're all doing great. I see a new student, Sridevi. Are you new, Kana?
Sir, this is Nandakishore. I'll just change my.
Okay, fine. Let me share my screen. Right. So we were doing aldehydes and ketones. Okay, so we were doing chemical properties, if you can remember. I think we finished with nucleophilic addition reactions, acetals, hemiacetals, HCN, ammonia derivatives, and then we saw reduction, right? And I told you the common reducing agents can be LiLH4, NaBH4, and H2 bar nickel, right? Aldehydes will form primary alcohols, ketones will form secondary alcohols. And there is one special thing about an LiLH4 and NaBH4 that is not going to affect C double bond C or C triple bond Cs. Whatever was there in the product, reactant, that is going to stay in the product. And then we saw about oxidation. Right, we started with oxidation. Like aldehydes can be oxidized to acids, whereas ketones cannot be oxidized further, right? And then last class, I think we saw the same very important reaction, that is your aldol condensation, right? So we saw different types: self aldol, cross aldol, intramolecular aldol, right? Intramolecular aldol, I don't think it is there in your syllabus, but still it is there, right? And then cross aldol we saw. And then we stopped with this Cannizzaro reaction. I told you this Cannizzaro reaction is going to be a disproportionation reaction. We know what are disproportionation reactions, right? One compound, same compound will get oxidized, that same compound will get reduced, right? And we have to understand that in aldol condensation, the requirement for the reaction to happen is that at least one alpha hydrogen should be there. If no alpha hydrogen means no aldol condensation, okay? But for Cannizzaro reaction, this will be given by aldehydes and ketones, which does not have any alpha hydrogen. I should not have any alpha hydrogen present. Only then Cannizzaro reaction is possible. Okay. And I told you that here the reagent uses again a base, but the only difference between aldol condensation and this one is that here we're going to use concentrated NaOH, right? There in case of aldol condensation, we'll be using dilute NaOH. That's the only difference here. Okay, so if you look at the reaction, you have benzaldehyde, which doesn't have any alpha hydrogen, right? In the presence of OH minus, I told you it is a disproportionation reaction. So two molecules of this, one molecule will get oxidized, that is your CHO getting over to COOH, and the same molecule CHO is getting reduced to CH2OH, right? And another example is HCHO. You have OH minus, again same thing, oxidation, HCOOH, reduction, CH3OH, right? So this is where we stopped last class. Now what we'll do is we'll look at the mechanism of this. How exactly is this happening? Even though it is not in a syllabus, very interesting mechanism. Okay, right? Fine. So people, right? So the mechanism of this reaction, right? See, we have seen that there can be three types of intermediates which can form, which can be formed in an organic reaction. Can you tell me what are the three intermediates possible, people? What are the three basic intermediates which are possible in organic chemistry? What are those? Go on. There are three intermediates possible in any organic reaction. Okay, right? What are the three common ones? Okay, if at all you're thinking what are intermediates, you have to think about maybe homolytic cleavage, nitrolytic cleavage. If I have homolytic cleavage, one type of intermediate.
Like phenoxide, sir.
No. Like you don't have to go for functional groups as such, right? Whatever be the functional group, whatever be the reaction, these three are common, right? Say if I tell you maybe one thing, you'll be able to do the other two. One is carbocation. What is the other two?
Carbocations, carbanions,
and
free radicals.
Radicals, sir.
Correct. So we have three basic intermediates, right? One is carbocation, carbanion, and free radicals. Remember that these are intermediates. Okay, these are what are called as intermediates in organic chemistry. Okay, so other than that, we have one uncommon intermediate. Okay, one uncommon intermediate called as carbenes. Okay, I don't know how many of you have heard this term, carbenes, right? So other than carbocation, carbanion, and free radicals, this is again going to be another important but very uncommon, very rarely you're going to see in these kind of intermediates in organic chemistry. Okay, so what are carbenes? Let me tell you before we move on to the mechanism. See, carbenes are going to have two bonds. Okay, I don't have to specify what are those bonds. Okay, like this. So we know that each and every carbon atom should have 4 bonds, tetravalent. Tetravalent should be satisfied, isn't it? So 2 bonds are satisfied, and the other 2 electrons are going to be as such, like this. Okay, so this particular species is what is called as a carbene. Remember, this is neutral. Okay, this is not charged, this is not negatively charged, not positively charged, it is neutral. Okay, so you should not consider this 2 electrons I'm drawing as lone pairs. Okay, rather you can consider this one as a diradical. We know radicals are going to have what? 3 bonds like this, and 1 electron is going to be the unpaired electron, right? So you're going to here, you're going to have 2 unpaired electrons, they're not paired. Okay, right? So these kind of intermediates are very, very common. Not common. These are one of the basic intermediates we can have in organic chemistry, but little rarely you will see in reactions. Okay, say one example can be this CH2 double dot, right? Or you can have CCl2 double dot. Okay, so these kind of species are what are called as carbenes. Obviously unstable. All intermediates are unstable. Yeah. Okay, so here in case of this one, in case of Cannizzaro reaction, 1 second. Are these going to be the intermediates here? No, I'm so sorry. I confused myself with Reimer-Tiemann reaction. Guys, you must have studied about Reimer-Tiemann reaction, isn't it? Right? In actually Reimer-Tiemann reaction, you will see that these are going to be intermediates. I'm sorry, you don't have to worry about it. Not to worry about it now. Okay. Anyways, now that you know new information, you can just remember it. Okay, don't worry about this. Okay. Right. Right. So people, what is going to happen in this? We understand it is going to be disproportionation reaction, right? Okay, let us take benzaldehyde, C double bond O with the H. Okay, right. So what is going to happen is first step is the heterolytic cleavage of the CH bond. Okay, it's the heterolytic cleavage of the CH bond such that H minus should come out. Such that H minus should come out. So basically you will break the bond in such a way that the hydrogen gets the 2 electrons are here. Okay, such that the hydrogen gets the 2 electrons which are here, right? So basically you will write minus H minus. Okay, right? So what will be remaining? We will be having this CO plus because carbon is going to have a positive charge because H minus is coming out, right? So now this you just keep it as such. Okay, fine. Or I can continue with this. Now what is going to happen from the base? Right, from the base we have OH minus. Okay, now this OH minus can attack the positive charge like this. Okay, so what is going to happen? We are going to have C double bond O is already there. Now comes the OH. Now one of the products you already sorted out. Right, one of the products first you removed a H minus from this and you added a OH minus to that. So you formed a carboxylic acid. One of the product is already sorted out. You can see one of the product is carboxylic acid, benzoic acid. Right. Okay. Now what are we going to do? Now this is one molecule. Second molecule we can take. We have to use 2 molecules. Right. We have a CHO like this. Okay. Now what is going to happen? Now we have this H minus, which was removed from the previous one, is going to come and attack this carbonyl carbon. I know this is a nucleophile. Right. I know this is an example for nucleophilic addition. Is it not? This is an example for nucleophilic addition. So if this attacks, obviously this bond will break. Okay. So I can write CH, another H coming from this, and we have an O minus. Okay, and from water, basically water is going to be there. So you're going to take a H plus, and that can be taken up by the oxygen to form what? CH2OH. Let us see CH1, H2, and this oxygen is going to have a hydrogen now. Okay, so product number 1, product number 2. Very, very simple. So first step is removal of H minus. If you make a H minus, there is going to be this kind of a carbocation form. Okay. Now to this carbocation, we have the base, which is going to act, it is going to give me OH minus. that is going to attack the carbocation to form this particular carboxylic acid. Very simple. Now you take the second molecule. Instead, now the second molecule is going to take up the H minus, which was cleaved here. Okay. Now that H minus is going to attack the carbonyl carbon nucleophilic addition reaction, and then obviously C double bond O breaks to form O minus, and then O minus accepts the H plus to form the corresponding alcohol. Okay. Mechanism is very simple. All right. Okay. Now what you have to understand is what if this is like see whatever these two reactions that you saw here, right? Both these reactions, right? Both these reactions are example of self-Cannizzaro reaction. How do you have self-aldol? Right? Why self-Cannizzaro? Because you're using two molecules of this, right? What if I use one molecule of one compound, another molecule of another compound, right? Now that is going to be what is called as cross-Cannizzaro reactions, right? That is what is called as cross-Cannizzaro reactions. Okay, so if I take that, so basically I'm taking 1 mole of benzaldehyde plus 1 mole of formaldehyde, and I'm going for OH minus, right? Now we understand that it is going to be disproportionation. I mean, we understand that one thing is going to get oxidized, the other one is going to get reduced. No doubt about it. Is it not, right? One thing is going to get oxidized, the other one is going to get reduced. No doubt about it. Isn't it, people? Okay. So if that's the case, we have to understand which will get oxidized, which will get reduced. Correct? Which will get oxidized, which will get reduced, we have to understand. Is it not? Right? So for that purpose, you have to look at the mechanism. If you look at the mechanism, right? If you look at the mechanism, there is one thing, right? There is one thing which is actually accepting H minus. If I take accepting H minus, it will not work like that. Okay, right, no issues. So what you have to understand is we are actually removing this H minus from this. So it is all about how strong this particular bond is, right? If whichever is going to have a stronger bond, CH or stronger CH bond, there it is going to be tougher to remove the H minus, and obviously it will not be able to give H minus. Rather, it is going to accept H minus. Again, I repeat whatever I'm saying. Right. So if we're talking about this CH bond is what we're talking about. If this CH bond is very strong, right? If this CH bond is very strong, we have to understand that this bond cannot be broken. Okay. If this cannot be broken, from this H minus cannot come out. Okay. That means whenever bond is very strong, you will not be able to give you'll not be able to break the bond and give the H minus. So rather what it will do, it will be able to easily accept H minus. Okay, rather than giving H minus, say you understand that one molecule is giving H minus and one molecule is accepting H minus. Okay, and you understand whichever is accepting H minus is actually the reduced product. Is it not? Whichever is actually accepting the H minus is what is going to be the reduced product. Okay, fine. So if that's the case, we have to understand that here we have this bond, this CH bond, and then here in this case, we have this particular CH bond, we have. Okay, now you can easily understand, people. You don't have to go into the details of which bond is stronger as such. You have to understand that the CH bond here is stronger CH bond. Okay, right? Fine. So if that's the case, if this is going to have stronger CH bond, this is going to accept, rather than giving H minus, this is going to accept H minus. Okay, rather than giving H minus, this is going to accept H minus. So obviously this is going to get reduced. Okay, this is going to get reduced. Okay, and obviously this one is going to get oxidized. Very easily we can tell this. Okay, right? Whichever is going to accept H minus is going to get reduced. Why is this accepting H minus? Because this CH bond cannot be broken because it is very, very strong comparatively to this, obviously. Compared to this, the CH bond is very strong. Okay, so now we can easily write that the product would be, this would have gotten oxidized, right? And the other one would have been like this. And this one would have gotten reduced. Okay, right? This is the very common question. Okay, common question they can ask. Formaldehyde with benzaldehyde cross Cannizzaro. Formaldehyde will get oxidized and benzaldehyde will get reduced to form benzyl alcohol. This is a common question which can be asked. Okay, so that is about Cannizzaro reaction. All right. Okay. So we completed aldol condensation. We completed Cannizzaro reaction. There are still more reactions left, right? I actually forgot certain reactions in oxidation, right? That we'll see now. Okay. Anybody has any questions here? Okay. Fine. I suppose everybody was following. Right? It's very simple, people. Whatever, only see these two are very common questions which can be asked in Cannizzaro, right? And another common question has been asked in cross Cannizzaro: benzaldehyde with formaldehyde. Formaldehyde oxidized, benzaldehyde reduced. That's it. That's all you have to remember. Okay, right. So the next thing is I forgot certain reactions in oxidation. Normal oxidation we saw, right? Normally oxidation, what happens when I have an aldehyde that will get converted into your corresponding acid that we saw already. Okay, now in this we can have certain tests, right? Under this, the first one is what is called as tolerance test, right? Under this, the first one is what is called as tolerance test. You have already studied about tolerance test in which chapter? Term 1, which chapter?
Biomolecules.
Biomolecules, right? We have something called as reducing sugars, non-reducing sugars. Whichever gives positive test for tolerance is what are called reducing sugars. Not only tolerance, we have one more. What is that? Tolerance and
Filling solution.
fillings, right? So the carbohydrates which gives positive test for tolerance as well as fillings are what are called as reducing sugars, and which doesn't give positive test for what are called as non-reducing sugars. That we already know. Now we'll see in depth. Right? What exactly? I mean, we have seen. I don't know whether I taught you the chapter. I don't remember teaching you, but still I'll teach you now properly in depth. Okay, fine. So in tolerance test, remember that this can be given only by aldehydes. Okay, right? This tolerance test, this is a test only for aldehyde. That means ketones will not give this test. Okay, ketones will not give this test, but your aldehydes only will give this test, except benzaldehyde. Okay, so benzaldehyde alone will not give this test, but all the other aldehydes will be able to give this test. Okay, only by aldehydes except benzaldehyde. Okay, but there are some special cases, right? There are some special cases where even some kind of ketones can also give this test. Okay, only one type of ketone can give this test, something called as alpha hydroxy ketones. Okay, so if you have alpha hydroxy ketones, not normal ketones, okay, if you have alpha hydroxy ketones, they can give positive test for tolerance and except tolerance and fillings both. In this case, we're talking about tolerance, so it can give positive test for tolerance. Okay, right. So what now? This was the reason why, if you can remember, fructose, right? Fructose was actually a ketose, right? It was actually having ketone functional group, right? But still, it was a reducing sugar. Right? Why? Because it was actually having what? It was actually having this kind of structure: CH2OH, C double bond O, something, whatever. Now you understand that this is a ketone, normal ketone, and this is your alpha carbon. Whatever carbon next to the carbon having C double bond is what is called as alpha carbon, and that alpha carbon was actually having what? It was having OH. Alpha hydroxy aldehydes and alpha hydroxy ketones will give positive test indeed for tolerance test. Okay, say if at all I'll give you an example. Other than fructose, we can have this one: CH3, CH2OH, CH3CO, CH2. Again, you see this is your alpha carbon having a OH. Okay, so only these kind of ketones, can give positive test for tolerance. But don't worry, questions are not going to be asked from this. Okay, all that you have to remember is, it is given, tolerance test is given only by aldehydes except for benzaldehyde. Okay, now other than that, some very few compounds can also give positive test for tolerance, right? One of them is acid, your formic acid, HCOOH, right? Can also give positive test. Another thing which can give is ethyne, CH triple bond CH. Okay, so other than that, nothing can give. Okay, so these are all some of the non-common things, right? This is generally and only for aldehydes, but other than that, very other few compounds can also give positive tolerance test, like alpha hydroxy ketones, formic acid, CH triple bond CH, ethyne. All those things are there, but don't worry about these things now. Don't worry about it. You have to concentrate only on aldehydes. Okay, right. So next thing what you have to understand is, what is tolerance reagent? Right? What is the reagent which you're going to use in tolerance test? Okay, tolerance reagent name, if I have to tell you, it is ammoniacal silver nitrate. That is the reagent which you have to use. Okay, Tollens reagent is ammoniacal silver nitrate. Okay, now the name looks very complex, but it is very simple, people. We have to take silver nitrate, okay, and dissolve it in ammonia, liquid ammonia. Okay, dissolve it in liquid ammonia. So if you do this, right, we are going to get a coordination compound. We will study about coordination compound maybe in the next chapter or after that. Coordination compound is going to look like this: Ag, NH3 twice plus NO3 minus. Okay, this is actually a complex. Right, we'll study in depth about coordination complex when you go for the chapter. But for now, you just have to understand that this is the product form. When I have AgNO3 silver nitrate dissolved in ammonia, that's why we call it as ammoniacal silver nitrate. Okay, now this is exactly a Tollens reagent. All right. Okay, so now what is going to happen? Say if at all I have an aldehyde, right? I have an RCHO, any aldehyde for that matter. Okay, and we take this Ag NH3 twice plus and NO3 minus. Okay, you don't have to mention it, no issues, right? So this is your Tollens reagent. Okay, now what you have to understand is this particular Tollens reagent, ammoniacal silver nitrate, is a mild oxidizing agent. We are studying, that's why we're studying it under oxidation. Okay, this is a mild oxidizing agent. Now we know whenever we have aldehydes, if I have an oxidizing agent, it is going to go for its corresponding carboxylic acid, isn't it? So this is going to be very simple. This aldehyde now will form RCOOH, no issues at all. Right now you understand that this entire reaction is going to be a redox reaction, in the sense that this is getting oxidized. Okay, so something has to get reduced, isn't it? This is one of the species getting oxidized, so something has to get reduced, and that something is getting reduced nothing but Ag. Now you understand that here Ag is in +1 oxidation state. Okay, Ag is in +1 oxidation state. So in the product side, Ag will get deposited. Obviously, it is going to have 0 oxidation state. So +1 to 0 reduction. This is reduced, right? And this is oxidized. Okay, now you understand that this is silver which is getting formed. Now this is going to be in the form of a silver mirror. Okay, so if I have to tell you what exactly is happening, right? So we have a test tube in which I have an aldehyde, for example, right? So when we add Tollens reagent to this, right, what is going to happen is I am going to form a precipitate of silver color mirror, silver color precipitate. This is your silver mirror. Okay, right? So if at all you form the silver mirror, if at all you form the silver precipitate, okay, that confirms the presence of your aldehyde in the test tube. Okay, if you are not forming the silver mirror, that means it is not an aldehyde, it is some other species. We cannot tell it is ketone. Please don't conclude that. Okay, if it is forming silver mirror, aldehyde, that we can confirm. If it is not forming silver mirror, it can be any other functional group other than aldehyde. Okay, right? That is exactly what is happening in the case of Tollens test. Okay, RCHO is there, getting oxidized. Okay, change the color. Getting oxidized to RCOOH, and Ag is in +1 oxidation state, will undergo reduction to form Ag precipitate, that is going to be in the form of a silver mirror, and this confirms, if at all you form a silver mirror, that confirms the presence of the aldehyde. Very, very simple. Okay, right? But remember that if at all I have benzaldehyde is an aldehyde, but with your Tollens, no reaction. Right? You don't have to go into the details of this. It is way above your level. Okay. All that you have to understand is benzaldehyde does not give Tollens test. Even though it's an aldehyde, that is the only aldehyde which will not give Tollens test. Okay. Right. So you understand that this is oxidation only. You are oxidizing your corresponding corresponding aldehydes into their acids. Okay. Right. Very, very simple. That is about Tollens test. You have to know what is Tollens reagent, you have to know the formula, how do you confirm it, silver mirror, all those things, everything should be there in fingertips. Very, very simple. Okay, that is your first reaction under tests. Okay, second one is what is called as Felling's test. Okay, Felling's test. Okay, now in Felling's test, what is going to happen? First, you have to understand what is, again, okay, fine. Felling's test. Felling's reagent. First, you have to understand what is Felling's reagent. Now, Felling's reagent is comprising of two reagents. Okay, two things, two solutions you have to mix to form your overall Felling's reagent. Okay, you have to mix something called as Felling's A, and you have to mix that with something called as Felling's B. Okay, you have to add them both, and that only gives you the entire Felling's reagent, overall Felling's reagent. Okay, what is Felling's A? What is Felling's B? Felling's A is simple. It is aqueous copper sulfate solution. I know this is going to be blue in color. Okay, aqueous copper sulfate solution is going to be blue in color. So I will take water, add copper sulfate, dissolve it. That's it, done. Your Felling's A is done. Okay, right. Next, what is Felling's B? Felling's B is sodium, potassium, tartrate. Okay, if you're wondering what exactly is this sodium potassium tartrate, fine. We have to know what is tartaric acid. Tartaric acid. Okay, so tartaric acid is going to look like this. It's going to look like this. COOH, CH, OH, COOH. Okay, this is what is the formula for tartaric acid. Okay, which you find in your tamarind generally, right? Tamarind contains tartaric acid. Okay, so this tartaric acid, if I have Na plus ion and K plus ion coming and replacing this H plus and this H plus, right? You're going to get, say for example, Na plus OO minus C, that is COO, Na, COO minus Na plus, CH, OH, COO minus K plus. That's it. Very simple. You removed one H plus, replaced it Na plus, you removed another H plus, removed K plus. This is basically an acid-base reaction. This is nothing but a salt. Okay, so this is nothing but your sodium potassium tartrate. You do not have to remember the formula or the structure of tartaric acid. Do not worry about it. I'm just giving you for your reference. Okay, all that you have to understand is Felling's B is nothing but sodium potassium tartrate. Okay, and this sodium potassium tartrate can also be called as Roche-Lase salt. Okay, it can also be called as common name. The proper chemical name is sodium potassium tartrate, and commonly it is also called as Roche-Lase salt. Okay, so you're going to take both these solutions, mix them together, and you're going to end up with your Felling's solution, overall Felling's solution. Okay, right. So people, now what exactly is going to happen in this test? Again, this Felling's solution, right? This overall Felling's reagent is again going to be a mild oxidizing agent, just like your tolerance. Mild oxidizing agent. So obviously, if at all I have an aldehyde, it is going to convert that aldehyde into its corresponding acid, right? Okay. So if at all I have an RCHO, and one more thing before we see this, Felling's test is given by all aldehydes. There is no exception here. All aldehydes will give this test. Even benzaldehyde will give this test. There is no exception here. Only for tolerance, there was some problem. Benzaldehyde was not giving that test, but Felling's, no problem at all. Felling's will give, all the aldehydes will give Felling's test, positive Felling test. Okay, there is no exception here. Okay, keeping that in mind, now moving on. So when we have RCHO, right, now they will not give you for Felling's reagent. They will not write Felling's reagent here. All they will write is they will have Cu2 plus ions. Is it not? Because we have copper sulfate, right? You can look at this. We have copper sulfate, so we are going to have Cu2 plus, SO4 2 minus, that is going to be present, right? Okay, so this Cu2 plus is going to be there. We know this one is going to get oxidized, right? And then this Cu2 plus is going to get reduced to form Cu2O, right? It is going to form Cu2O. You can understand that here copper is going to be in +1 oxidation state, right? This is actually reduced. Okay, your copper is in +1 oxidation state. So copper undergoes reduction, aldehyde undergoes oxidation, right? And this one is going to be a reddish precipitate. Right, this one is going to be a reddish precipitate, or you can even tell it as it is a brick red precipitate, single color, brick, right? Brick color precipitate. Okay, brick red precipitate. Okay, because of the formation of Cu2. Right, so when you form this brick red precipitate or reddish precipitate, that confirms that the whatever was there, the solution was nothing but an aldehyde. Okay, right? So we have RCHO getting oxidized to RCOOH. Cu2 plus ions that are there in the solution will get reduced to form Cu2O, which is going to form reddish color precipitates, and that confirms the presence of aldehydes. Okay, right? So that is about your Felling's test under again oxidation, right? So we saw normal oxidation, right? Now we saw Felling's test, we saw Tollens test, and there is just one more very, very important oxidation reaction. Okay, that also we'll see. Maybe you might have seen this in your aldehydes ketones chapter, but again we'll see. The third one is what is your iodoform reaction. Okay, the third one is what is called as your iodoform reaction. Okay, first of all, what is the formula for iodoform? Do you know?
CH3.
CHI3. Good. Okay, so in this reaction, people, we are actually going to produce or form a iodoform. Okay, in the product side, you will see that one of the product formed is going to be iodoform. Okay, and you have to understand that this one will be an yellow color precipitate. Okay, the CHI3 will be an yellow color precipitate. Okay, and this can also be used as a test, not only for aldehydes, but for anything test for this particular say chunk. CHO means CO, CH3. Obviously, another bond is there, right? Right. So if at all you have this particular functionality, C double bond O, and to that C double bond O, there should be a methyl group attached. Okay, those kind of aldehydes and ketones can only give this test, that is your iodoform reaction test. Okay, so if I ask you CH3, CH2, CHO, will this give iodoform test? Will this give iodoform reaction? What is your answer? Wait, don't answer. Just go to your chat box, okay, people, and just type yes or no. This particular thing, whatever I wrote, right, will it give iodoform reaction or not? Right, this one. Just type yes or no in your chat box. Go on, like it is just a guess game. Everybody can answer. Right, whatever I wrote now. What did I tell you? Like again, I repeat, right? I told you that you should have C double bond O with the CH3 should be there. And this, if it is there, yes, it is going to give iodoform reaction. If not, it is not going to give iodoform reaction. Right, now look at this compound and decide whether that is going to give iodoform test or not. Okay, yeah, now you can go answer the question, yes or no.
So this is specifically for CH3 or any alkyl group, sir?
No, only for CH3, specifically for CH3. Okay, Sashank says yes, Rohan says no. Okay, come on people, we have 15 students here. You need not be right, you need not be wrong. It is just a guess game. I don't expect you to give correct answers always. Go for it. Okay, Anandita says no. Go on, go on. I'll give you 1 minute for everybody to put their answers. Okay, Ananya says no. Nanda Kishore says no. Aksha says no. Okay, right. Okay, Mithun says maybe. What is that answer, sir? Maybe. Okay, right. So people, what did I say? You should have, you compulsorily should have you should have a C double bond, obviously, but to that a methyl group should be attached. CH3 should be attached. You can also tell that it is a test for alpha methyl groups. Right? I should have an alpha methyl group for this reaction to happen. That means what? This is your main carbon. Okay, the next carbon should be a methyl group. That's all I'm trying to say. Okay, now you understand that this is your main carbon, and you understand this is not CH3, this is CH2, right? So this is not, definitely not going to give your iodoform test or iodoform reaction. Okay, right? But if I ask you whether this one will give CH3CHO, will this give? Yes or no? Anybody?
Yes, sir.
Yes, right? This will definitely give, because I have the C double bond, right? How will you write the proper structure? We have the C double bond with the H, and we directly have a CH3 attached to this. Yes, this will definitely give. What about this one? CH3, C double bond O, CH3. Will this give? Yes or no? Quick, quick, quick. What is it? Will give?
Yes, sir.
Yes, right. Because we have a C double bond O. Directly we have one, not only one, but we have two CH3s. Right? Only at least one is there. Enough. We have two CH3s. Definitely this will give iodoform test. Okay, fine. So now what are we going to do with this alpha methyl groups? We'll try to understand now. Right? Okay. Now people, the reagent used, right? The reagent for this reaction is NaOH plus I2. Okay, iodine plus NaOH. Okay, that is your reagent. Okay, now I don't know whether you remember from P block, right? Whenever you have this NaOH plus I2, you are always going to form NaOI. Okay, NaOI. This is actually the thing which is going to be used up in the reaction. This is prepared in situ. Can you tell me what do you mean by in situ preparation? Anybody knows what do you mean by in situ preparation? Okay, right. So people, some of the reagents, or say something I want to use in a chemical reaction. Okay, I want to use one particular thing in a chemical reaction. Okay, but that particular thing which is going to be used in the chemical reaction is very unstable. That means you cannot store them. Okay, for example, this one, right? This one is highly unstable and you cannot store it. NaOI solution, how do you store NaCl solution? How do you form HCl? How do you store HCl solutions? Like that, you cannot store these kind of solutions that are unstable. Okay, so since it's unstable, since I'm not able to store them, but still I need them for the chemical reaction to happen, right? So what I do, I prepare them like during the course of the reaction itself, right? I prepare them. Like I just put this NaOH and I2 together, and that is going to produce this, and that is going to eventually react, right? Before it is going to become, like say, the unstable behavior, before it is going to show, that is going to react with the compound. Okay, so these kind of preparations are what are called as in situ preparation. Whichever is unstable and we are not able to store them, we prepare it then and there and use them directly, right? That is what is called as in situ preparation. Okay, right. So whether they give NaOH bar I2 or whether they give NaOI, they are referring to iodoform reaction only. Okay, right. So what? Just one moment. I'll just close the door. Okay. So let us see what exactly is going to happen in this reaction, people. Right. So let me take this C. Okay. Before I move on to this, let me give you the shortcut. Okay, right. So we understand that this reaction is going to be given only by groups which are having this C double bond O CH3. Whatever be the group here, whatever I'm going to tell you is going to be common. Okay, right. So to this, if I put NaOI, or I can also represent it as NaOH in the presence of I2, whatever it is. Okay, and one more thing, this particular thing, NaOI, is what is called as sodium hypoiodide. That's the name of the compound. Okay, sodium hypoiodide. All right. Okay. So whether you directly give you, I write sodium hypoiodide or I write NaOH in the presence of I2, as I've mentioned, we are talking about iodoform reaction. Okay. Right. So what is going to be the product? I told you that only these kind of groups can give. There is one extra bond which is going to have something else. Don't worry about it for now. Okay. So people, this particular one, the CH3 which you're seeing, right? Okay. Now that black color which I'm marking, that CH3 is going to convert into CHI3. Okay. That CH3 is getting converted into CHI3, and I know this is going to be yellow in color. Okay. Right. Now select me some other color. Now this C double bond O and this entire group. Okay. Now that one is going to become C double bond was already there. One bond is already there. To that, what you do is just you add a OH to that. Very, very simple. Again, I repeat. You have the C entire thing. This entire group is there. Okay. Now that I'm writing normally. C double bond is there. One more bond is there. To that, you just add a OH. Very, very simple. So this is nothing but a carboxylic acid. Okay, so in all the iodoform reactions, there will be two products. One is your iodoform, which is yellow in color. right? The other one is going to be the carboxylic acid. Okay, right? So remember that the CH3 attached, the CH3 attached to the C double bond O will get converted into CHI3, that is yellow, yellow in color, and the other part, that is C double bond O with the other part, that is going to convert into your carboxylic acid. Very, very simple. Okay, if I give you an example, it will be easily able to understand. Okay, say for example, if at all I have CH3 C double bond O with the H, that is CH3CHO. Okay, and I'm going for NaOH in the presence of I2. Now, what did I tell you? The CH3 attached to the C double bond O will form CHI3. Okay, right? What is remaining now? What is remaining now is this part. Just write it as such. I have a H and I have a C double bond O. One extra bond should come, and that extra bond is nothing but OH. Very simple. You understand this part. To this, I just added a OH. Right? So these two will be the products. Okay, right? So this I'll be able to rewrite it as HCOOH. Very, very simple. Okay, right? So if I give you another question, will you be able to solve? Say if I give you this particular carbonyl compound CH3COCH3 in the presence of NaOI, in NaOH, in the presence of I2. Tell me what are the two products, people. You can take any one methyl group, convert it into CHI3, other methyl group, keep it as such. Right. And you can send me in WhatsApp what is the product, or you can just tell me, you can just unmute yourself and tell me what is the product. This much time. I told you what you have to do.
Since
No, you send me. Okay. Okay. CH3, COOH, and CHI3. Yeah, correct. Right. So I don't know.
No possibility of two compounds, no, sir.
Yeah, because both of them are CH3s, right? Don't worry about it. You just there are only two products. That's it. One is CHI3, the other one is acetic acid. That's it. Done. Okay. Right. So people, first one, I say you can either you can take this one or this one. Let me take this one. Okay. Now this one I know is going to form CHI3. Done. So the other color will let us use this entire part. Now let me write it as such. CH3 is there, C double bond O is there, one more bond has to come, and that is going to be OH. Very, very simple. Done. So these two are going to be the products now, CHI3 and acetic acid. Okay. Now one more reaction. Right. Let me see this time at least more people should be sending me the answers. Go for it. Okay, I'm sorry. It is NaOI.
Sense.
Yeah, okay. Yes, someone wants to say something? Someone was trying to say something? Yes.
Yes, sir. Sense.
Okay, okay. No, other than Rohan, someone was trying to say something, I guess. Okay, fine. Yeah, Rohan, yours is correct. But look at it should be a 6-membered ring, but you have written only 4-membered ring. See, 5-membered ring. That's the only mistake. Other than everything is fine.
Yes, sir.
Yeah. Okay, anybody else wants to give me an answer? People, please do not sit idle. Right, the organic chemistry, the entire thing is about writing and getting the products. Right, do not sit idle. Maybe I'll give you 30 more seconds. Maybe someone can unmute yourself and tell me the answers. Did you have school today, guys?
Sir, yes, sir.
No, that's why you're tired. Okay, another answer. Ananya. Ananya, you did the exact opposite, Ananya. CH3 should be converted to what, Ananya? CH3 should be converted into CHI3.
Okay, sir, I'll change.
Right? And good attempt, good attempt. Okay, another thing came. Okay. CHI3, who's this? Anandita? Okay, Anandita. Yeah, yours is right. Okay, right, good, good. So very simple, right? So we have to convert this CH3 attached with the C double bond O to your CHI3. Very good. And just write the other thing as such, right? This part, we just write it as such, right? We have a benzene ring with one C double bond O. Okay, and I told you to the C double bond O, what you have to add is a OH. Done. That's the answer. Okay, very, very, very simple reaction. Okay, and you have to understand that all the CHI3s we forming, those are all yellow in color, and that is why it is going to use the test for COCH3 group, C double bond to CH3. If it is there, those kind of things will give yellow color in the iodoform reaction. Okay, I hope everybody is following, right? So did I miss any reaction yet? Yeah, we have a little more reaction to see. Right, so that is about your oxidation reactions. Okay, we have seen normal oxidation, Tollens test, Felling's test, and iodoform reaction. 4 reactions under oxidation. Right, and then I forgot one thing about reduction. We saw about reduction, but again we saw only normal reduction. Right, we saw reduction to alcohol. Right, we know reduction to alcohols, which we have already seen. Reduction to alcohols, we know that is, say for example, if I have CH3 CHO, say I go for H2 bar nickel. Right, we are going to form CH3 CH2OH. Right, say if at all we have a ketone, say I go for LiAlH4. Right, I know we are going to form a secondary alcohol like this. Right, now that is this we already know, this we have already seen. Right, now what are we going to do is we are going to go for reduction to hydrocarbons. Reduction to hydrocarbons. Okay, right. So in this case, what are we going to do? We are going to take your carbonyl compound, that is C double bond O. Okay, and then we are going to go for some reducing agent we are going to use. Okay, and I'm going to convert this one C double bond O into CH2. Right, we are just going to remove the oxygen and put 2 hydrogen atoms there. Okay, that is why we say it is getting reduced to normal hydrocarbons, alkanes. Not only alkanes will come. Okay, right. So under this we have 2 reactions. 2 named reactions are there. First one is what is called as Clemencens reduction. Right, first one is what is called as Clemencens reduction. Okay, so in Clemencens reduction, what are we going to do? We are going to take this, like, to both the reactions, same product, except that what is the reducing agent used? That is what is going to change. Okay, right. So here, people, in Clemencens reduction, we are going to use zinc amalgam in the presence of HCl. When I write ZnHg, means it is called zinc amalgam. Okay, so before we move on to see what exactly is happening, people, can you tell me what do you mean by an amalgam? What is an amalgam? Don't tell mercury. Just
Compound formed by mercury.
come again. Sorry.
Compound formed by mercury.
Compound formed
Sir,
by
mercury plus any other metal to form an alloy. It's called as amalgam.
plus any other metal to form an alloy. Okay, I can take this as a little more closer answer. But first one, not compound. This is not a compound. Okay, this zinc amalgam. This is not a compound. This is I can say it's an alloy. Okay, that is a better answer. Any other answers? Any other answers? Anybody wants to give? Can I call alloys as solutions? People, can I call them as solutions? Recall solutions chapter. Can I call alloys as solutions?
Solid and solid.
Yes, sir.
Yes, they are solid and solid solutions, right? So, like, anyways, don't worry about it. So the thing is, people, amalgam is a solution. Amalgam is a solution in which Hg is the solvent. I know Hg is going to be in liquid state. I know that's the only liquid metal, right? So if at all you use mercury as a solvent and you dissolve some other metal in that, you dissolve that, and that particular alloy or that particular solution which you're going to get is what is called as your amalgam. In this case, it is zinc amalgam, means zinc is dissolved in mercury. Okay, right. Anyways, so we have to use zinc amalgam in the presence of HCl. So what is going to happen? We are going to convert the C double bond O to CH2. All right. Okay, so let us take some proper examples. Say, if at all I have a cyclohexane ring with a double bond O, wherever you see double bond O, just remove it and put hydrogen, right? So if I go for zinc amalgam in the presence of HCl, all that we are going to get is cyclohexane. Basically, we understood there are two hydrogens here coming up. That is understood. Okay, right? Say another example. Say if at all I take CH3, C double bond O, CH3, and then I go for zinc amalgam in the presence of HCl, nothing, just convert your C double bond O into CH3, sorry, CH2. That's your product. Okay, right? Fine. So that is about Clemencens reduction, right? The same thing is going to happen, exact same thing is going to happen, right? But fine, we'll see this. Okay, exact same thing is going to happen, but the reagent here it is zinc amalgam bar HCl. In this case, we are going to use some other reagent. Okay, and that reaction is what is called as Wolff-Kishner reduction. Okay, that reaction is what is called as Wolff-Kishner reduction. Okay, so in Wolff-Kishner reduction, the same thing we'll do, that is C double bond O. 2CH2 is what we are going to convert, no doubt about it, right? But the reducing agent, look into this. The reducing agent is NH2NH2 in the presence of a base, OH minus. People, this NH2NH2, it has a name and we have already seen it. What is the name of the compound? NH2NH2?
Amine.
Amine? No, Amine we didn't see. Amine is yet to come for you. This is an ammonia derivative, is it not? Because we have NH3, we have replaced one hydrogen with NH2. This is an ammonia derivative. What is the name of the derivative?
Hydrazine.
Hydrazine. Yes, it's called hydrazine. Okay, so we have to use the reducing agent has hydrazine in the presence of a base. That is what is going to happen. Okay, right. So let us take some examples. Say if at all I have CH3CHO in the presence of NH2, NH2OH minus, I know I'm going to form CH3CH3. That's it. Wherever you have C double bond O, convert it into CH2. Plus hydrogen is already there, so CH3. Okay, say another example. Say if I have this one, a cyclohexane ring with C double bond O CH3. Again, if you go for NH2 in the presence of OH minus, again, very, very simple. You will convert the C double bond O into CH3. Okay, very, very simple reaction, right? So this is what we have for reduction to hydrocarbons, two reaction. One is your Clemencens reduction, that we use zinc amalgam in the presence of HCl as the reducing agent. And second one is Wolff-Kishner reduction, where we use NH2 NH2, that is hydrazine, in the presence of a base as the reducing agent. Same product is same. Okay, right? So that is about reduction. Any other reaction I missed? Okay, fine. I think these are all the reactions, right? Yeah. So now we can go for the benzene compounds. Okay, just check people if I have missed any reaction. If I have missed any reaction, please let me know. We'll see that. Not a big deal at all. Okay, fine. So next one is when we go for how to produce your benzaldehyde, say benzene with ketone. How do you produce all that? Let us try to understand first. Okay, so now we are going to go for aromatic carbonyl compounds. Okay, aromatic carbonyl compounds. Let us see the preparation first. Okay, so first one, okay. First one is what is called as, again, a name reaction, Gattermann-Koch reaction. Okay, Gattermann-Koch or Gattermann-Koch, however you want to call it. I think it's Gattermann-Koch. The CH is Koch. Okay, it's a German name. Okay, that's why they have some very weird pronunciations. Okay, so what we are going to do here is we are going to take benzene, okay, and we are going to react CO and HCl to this. Okay, CO and HCl to this, and we are going to directly get benzaldehyde. We are directly going to get benzaldehyde. Okay, people. There was another method, another name reaction by which we were able to produce benzaldehyde. What was the name reaction? Can someone tell me?
Cold reaction.
What reaction?
Cold.
Kolb's reaction. Okay, Kolb's reaction with phenol, right? No. That is salicylaldehyde you're talking about, right? Not that. Only this. Only benzaldehyde. Again, and that is with phenol, only this. All your answers are correct. I will not say wrong, but only I want this. Benzaldehyde only I want. In this chapter only we saw, in the preparation part. That was a name reaction.
Could you repeat the question once?
Sorry?
Could you repeat the question once?
I'm telling there is another name reaction by which you'll be able to prepare benzaldehyde. This is what is called as benzaldehyde. Right? Another name reaction was there. We saw in the preparation of aldehydes. We saw that actually coming up. What was the name reaction? Okay, I'll give you one more clue. The name reaction starts with E. E for elephant. What reaction?
Etat.
Etat reaction. Okay, what happens in that Etat reaction? Can you tell me? Go on, guys. Check your notes. Check your textbooks.
Benzene with methyl will react with CrO2Cl2.
Okay. What is it called as? CrO2Cl2 is what is called as?
Bromyl chloride.
Very good. Bromyl chloride. Right, so we are going to, this is toluene, CH3, right? Toluene should be there, not benzene. It is prepared from toluene. Okay, you can just take the reaction as Etat, second reaction. Okay, so we are going to produce, I'm sorry. We are going to produce CHO like this. Okay, right? So two reactions you have to remember for preparation of benzaldehyde. Okay.
I have a doubt, sir. We can just use any one of this reaction also. So what's the use?
Any one reaction you can use, but you have to know the reactions, right? These are there for your exams. Both reactions you have to know, right? Say if they will not ask you in the question, in the exam, like what are the methods by which you'll be able to produce benzaldehyde? They will give the question like this. If I have this one, right? It is reacting with CO in the presence of HCl to form A. It is reacting with it's reacting with say HNO3 plus H2SO4. It is forming B. Like that, they'll ask you to find A and B, right? So it is not about what to say. It is not about knowing only one method or two methods for the preparation. You have to know all the methods because they'll not ask you write all the methods of preparation of benzaldehyde. They'll ask questions like this only. Okay. Right? Good. Moving on. So 2 reactions for benzaldehyde preparation we saw. Let us see how to produce your this thing. What is that? Ketones. Okay. There is only one simple reaction, people. Right? That is your Friedel-Crafts. Can you finish it? Friedel-Crafts dash what? Friedel-Crafts
Alkylation.
Alkylation. Acylation. Yes. Okay. So what we do here, say we have benzene, right? What you have to use is R C double bond O Cl, right? In the presence of AlCl3. In all the Friedel-Crafts reactions, this is common. This is your Lewis acid. Okay, and this all Friedel-Crafts reaction, not only acylation, any reaction for that matter, any Friedel-Crafts reaction is actually going to be an electrophilic substitution reaction. Okay, all the Friedel-Crafts reaction, or not only that, any reaction with benzene, any reaction with the benzene or its derivative will always be an electrophilic substitution reaction. Basically, what is going to happen? We are going to replace, or in general, I can write. So electrophilic substitution means we are going to have all the things are having hydrogen, right? All the 6 carbons are having hydrogen. So one electrophile is going to replace your H plus, right? So we are going to do an electrophile here, and the H plus is going to move out. That is what is electrophilic substitution. One electrophile replacing another electrophile. One positive charge replacing another positive charge. Okay, right. So what is going to happen here? Here also the same thing is going to happen. One H here is going to get replaced with your C double bond O. Yeah, your C directly. What is attached to the benzene ring? Directly attached C double bond O with your R. And this R can be CH3, C2H5. It can be anything. Okay. Now, how exactly this reaction happen? We are saying that there is an electrophile produced. Right? There should be some kind of positive charge. Only then we will be able to have this kind of reaction happening. Isn't it? So how exactly this reaction happens? Let us try to understand. So we have this RCOCl, right? And that is going to react with AlCl3. I know that AlCl3 is going to be acting as a Lewis acid. I know all Lewis acids are electron pair acceptors. Right? All Lewis acids are electron pair acceptors. Okay, so what is going to happen is I am going to remove Cl minus heterolytically from this. You understand that heterolytic cleavage electron goes to chlorine now, right? So Cl minus comes and that Cl minus goes and attacks the AlCl3, donates its electron. Cl minus has the 2 electrons, lone pair is there. That lone pair is going to be donated to AlCl3. So in that process, what is going to happen is you have removed electron from this carbon. So we will have RCO plus, right? Plus AlCl4 minus. That is what is going to happen. And this one, that is, why is my benzene rings looking so bad? Okay, so now we have the benzene ring. Now you have the electrophile coming RCO plus, and that is going to attack here, replace the H plus to form C double bond O with 1 R. That's your ketone. Okay, very, very simple reaction, right? You have to understand that this is the electrophile which is coming, and you understand that the carbon atom which is having the double bond is only having the positive charge. So that only should be attacking the benzene ring. That's why we're making a bond between benzene ring and the carbonyl carbon. Okay, this is your Friedel-Crafts acylation. Okay, right. So these are the various methods by which you'll be able to produce your corresponding aldehydes or ketone, aromatic aldehydes or aromatic ketones. Okay, now maybe if I give you one reaction like this, I have benzene and I'm making tell me what is the product. So the R is what is changing here. The R is now what? Benzene ring. So I think
it forms two benzene and one C double bond
in between, right? Yeah, absolutely. This would have been the product, right? And this particular product is what is called as benzophenone. Okay, because we understand that the electrophile would have been what? Electrophile would have been this C double bond O plus, and this would have attacked the benzene ring to form this particular product. Very, very simple. Okay, right? Fine. So these are all the different methods of preparation of aromatic aldehydes and aromatic ketones. Now let us check the chemical properties. Okay. Yeah. Any questions anybody has? Okay. Right. So before I move on to the chemical properties, I want you to write the resonance structures. The resonance structures of benzaldehyde. Or any other, you can even write the resonance structure for any aromatic aldehyde, any aromatic ketone, everything is going to be same. Okay, let me write this properly. Okay, I want you to write all the resonance structures possible for this particular aromatic compound. Go for it, and you can send me in WhatsApp. I'll give you 5 minutes time. Okay, I hope you guys are not sitting idle. Okay, I don't know whether it's that difficult or not. So does somebody need any more time, or can I solve it? Anybody is doing and they need more time? Okay, fine. I take that as a no. I mean, I take no as an answer, and let me help you with this. Okay, fine, people. So we have C. Okay, C double bond O with one H. Right now, the first step of the resonance structure should start from this double bond. Okay, now this double bond will directly shift here, and then this bond will break. That's the first step, right? Okay, if you do that, right, what will we get? We will get CO minus, right? And this double bond shifted to this carbon, and this carbon, nothing happened. Basically, a bond is broken from here. Again, the same bond is formed here. No issues, right? But what about this carbon? This carbon has lost electron, so that carbon will now get a positive charge. Okay, right. Now other thing stays as such, right? Next, what is happening? Now we can shift the double bond here. Now shift the double bond there. So now what is going to happen? We have CO minus, and there's a double bond here. Now there is a double bond here, and now this carbon has lost electron, so you put a positive charge there, and this is there. Another bond is there. Now what will you do? You will put this double bond here. Okay, so when you put that double bond there, we will have O minus. There's a double bond here. There is already a double bond here. Now you have kept a new double bond here, and you understand that this carbon is now going to get a positive charge like this because it is losing electron. I'm doing something wrong, right? Yeah, exactly. This is, I have a carbon that is having O minus, and this is having a double bond, and that is having a hydrogen. This is having a hydrogen. This is having a hydrogen. I'm forgetting the hydrogens. Okay, right? Okay, what is the last step? Last step is everything coming back to the original position. So this will come back, make a double bond here, and this double bond will shift here, make a double bond here. So we will have C double bond O with a H. Now there is a double bond here, and a double bond here. Okay, now these are all the possible resonance structures we can have for benzaldehyde. Not only for benzaldehyde, say if at all it was any other group other than say CH3, some other benzene ring, whatever is there, this would have been the resonance structures, no doubt about it. Okay, now why did I spend so much time on mentioning these resonance structures? Is that now when we go for electrophilic substitution, I told you benzene and its derivatives. Okay, benzene and its derivative will generally go for electrophilic substitutions. Correct, right? So that means there is going to be one positive charge coming, and that is going to replace the hydrogen. Basically, there are hydrogens here, not this hydrogen. Okay, any other hydrogen other than the other 5 hydrogens can be there. That hydrogens can be replaced. Okay, Now the question is, which hydrogen is going to get replaced is the question, right? Which hydrogen is going to get replaced is the question. Now you understand that if the electrophile is approaching, right? If the electrophile is approaching, you are seeing that it is actually going to face repulsion. Is it not? It is actually going to face repulsion because there's already positive charges. According to the resonance structures, we are seeing that there are positive charges developed on the benzene ring. Correct? So when the electrophile is going to come, that is already a positive charge, and I have positive charge already there on the benzene ring, so you will have repulsions happening. Okay, so that is why we say that this C double bond O group is actually a deactivating group. What do you mean by deactivating? It is less reactive. It is less reactive towards electrophilic substitution reaction. That is what you have to understand. Okay, they are less reactive, not like phenol. Phenol is very, very highly activating group. You understand? Because when you look at the resonance of phenol, you will form negative charges in the benzene ring. I don't know whether you have noticed it. Okay, very high negative charges. So it is going to be very, very highly reactive for the incoming nucleophile. Right? But here you are forming positive charges. So the incoming electrophile will actually have so much repulsion experienced. All right, that's why we say they're going to be deactivating groups in the sense that they're going to be less reactive towards electrophilic substitution reactions. Okay, but they're less reactive doesn't mean that they are not reactive at all. They will react. Okay, now the question is, the electrophile will go to which position? That means, say if I have benzaldehyde, C double bond or CH3, so benzaldehyde or anything for that matter. Okay, now say I have an electrophile coming. Now you have three positions possible. We know that ortho position possible, or this is your meta position possible, and this is your para position which is possible. Three positions are possible: ortho position, para position, or meta position. Okay, now you understand from the resonance structures that in the ortho position, para position, and in the ortho position, you can understand ortho, para, ortho, 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 para, ortho. You are seeing that there is already a positive charge, right? So it is impossible for the electrophile to go and attack in the ortho and para position. So it will try to suffer minimum repulsion and go make the reaction happen, right? So obviously this will go attack the meta position only, right? So if at all you have this C double bond O, CH3, this is where you'll get the electrophile meta product as the major product. Right, and you can also tell that this C double bond O group is actually going to be a meta directing group. It is going to be a meta directing group. Okay, in any electrophilic substitution, the moment you see that the C double bond attached to the benzene ring, the incoming electrophile will go to the meta position only. Now you know the reasons also. Why? Because according to the resonance structures, in the ortho and para positions, we have a positive charge, so the electrophile cannot go there because it is going to suffer repulsion. Positive repulsion. All right. What is the time? Okay, we have 5 minutes. Right. So let us see what are all the different reactions. You have already known the reactions. Let us see. First one is say Friedel-Crafts. Actually, this is not going to undergo Friedel-Crafts reaction. Right? We don't have to see this. Okay, fine. Actually, you can take a note. The note is that your benzene, your aromatic hydrocarbon, aromatic carbonyl compounds, will not give Friedel-Crafts reaction. Friedel-Crafts reaction. Right? Why is the question? Right? Friedel-Crafts reaction. Why it will not give? Now the thing is, right? You know, in any Friedel-Crafts reaction, I know one something should be there, and we are going to use a Lewis acid AlCl3. Okay, now what is going to happen is I know that this AlCl3 is actually the one who is responsible for producing the electrophile. Is it not? This AlCl3 is the one who is actually going to be responsible for the electrophile to be produced. Okay, so but actually what is going to happen is we understand that there are lone pairs present on this itself. This oxygen actually possesses lone pairs, right? Now that will react. okay, that will react with this, right? And eventually, whatever has to form, the electrophile which has to form will not form at all. I hope you know, I hope you are able to understand what I'm trying to say, right? There should be something that reacts with this to form the electrophile, right? And that electrophile will go and attack the benzene thing and something will happen. But before even this reacting, this lone pair on the oxygen itself will react with the AlCl3 and eventually no further reaction will happen. Okay, right? But nitration can happen. For example, say C double bond O, H is there. And then if you go for HNO3 plus H2SO4, I know this is your nitrating mixture, right? So we are going to get meta products. CHO is there in the meta position. I'm going to have one NO2, right? So even if this happens, even if Friedel-Crafts reaction happens, say for example, say we go for C double bond O CH3 is there, and then we go for say CR Cl in the presence of AlCl3. We know this is nothing but alkylation, Friedel-Crafts alkylation, right? So now you have to understand that even if it happens, it will not happen, but even if it happens, right, we are going to have the product coming only in the meta position. R will go to the meta position only because that would have been the electrophile. How? You have RCl reacting with AlCl3. Again, same thing. Cl minus will come, right? So you will form R plus AlCl4 minus. So this is the electrophile that will go and attack, and this is going to be the product. Okay, so at the end of the day, what you have to understand is your carbonyl carbon attached to the benzene ring is always going to be a meta directing group. That is what you have to understand. Okay, right? So people, we have successfully completed aldehydes and ketones only. We still have carboxylic acids. So next class, what we'll be doing it, we'll be solving a lot of questions on aldehydes and ketones from preparation. From this, all the reactions we'll be solving questions. And then we'll be moving on to carboxylic acid. So revise all these reactions and come back. Whatever reactions you have seen, so many reactions you have seen, you can revise all these reactions and come to the class. So that is, I think, on Sunday. Okay. And then we'll be solving a lot of questions. At that time, don't come and blink. What reaction is this? What is the reagent? All these don't come and blink. I will ask you individual questions. I'll not ask, it is not going to be a group question. I'll ask maybe say individual student to solve and send it to me in WhatsApp or answer this question. Okay, right? Maybe if you want, I can send this PDF. Do you want this PDF? This entire thing, page?
Can you send it, sir?
Yeah, I'll send it. You can go through that and you can study your book also, right? And you can come and we'll solve questions from this, only from aldehydes and ketones. Forget about carboxylic acids for now. We'll see that later. Okay.
Okay,
fine. Rohan, I'll just send you. Can you share with everybody?
yes, sir. No problem.
Because there is no group.
Can I just forward it in the chemistry group, sir?
No, I'm not in the group. No, that's why. If I'm there in the group, I'll directly forward it there. I'm not there in the group.
No, sir. Shall I forward it there?
Yeah, you can forward it. Whatever, in whatever means, everybody has to get it. That's all it is.
Yes, sir.
Okay. Okay. So let me print this. Will take some 2 minutes, okay, because it's a very big file. Okay. Okay, so it will be sent, and Rohan, you can share it to others.
Yes,
Okay.
yes, right.
Right. So guys, come prepared for the, not a test, but it'll be nice if you prepare and come. Please don't come and blink. It'll be very boring if you don't prepare and come. Now only I'm telling. Okay, fine guys. We'll see you on Sunday. Thank you so much.
Thank you.
Thank you.
Thank you.
Thank you, sir.
Yes.